Yes. So when he's there, everybody should be present. Of course, to give the presentation as well, you should be present. Okay, so now the chemical reactions. That's the topic today. And you can, of course, ask if you need some to, about the course or also the chemical reactions. But this should be pretty, so it's pretty basic all the time. Maybe some of you are already experts in this. I don't know. I should do some kind of a survey in the beginning, but no, it didn't happen. And also I'm teaching this topic first time in English so that I might not be perfectly fluent. Also, these slides are translated from the slides of the course in Finnish, so there might be something a little bit like most of it's so like good English, but there might be some little things that are maybe not. Okay. Because also the book of the course is still a book in Finnish. But these things are, of course, so basic chemistry that this should go with that as well. So the chemical reaction there, the things that we cover on this lesson are listed here. How you form the equation for the reaction, then you don't lose any substances there. This sounds really law of the indestructibility of matter. Sounds really impressive. Then, well, of course, you have to balance the equation so that you don't lose or gain something that you shouldn't. Molar rations of substances you get from the equations, and then you can calculate how much you need something to get something out of the reaction. Endothermic and exothermic reaction, for sure, maybe these words are already familiar to you. Reaction balance, Le Chatelier principle, this, well, we quickly cover this as well. Precipitation reactions, if you get some kind of a precipitate when two liquids react together. Oxidation and reduction reactions, these are also then in the electrochemistry. But because the topic is chemical reaction, and this is all the things that also the course book covers in this topic. Okay, so we know that elements are substances that consist of only one type of atom. And this is also something that the presentations will be about. Some kind of a element of that you have chosen yourself that you want to tell, you are interested in and tell about for the rest of us. So there, for example, hydrogen, oxygen, carbon, yes, they are elements. But then there's currently 118 elements that are known, and of these 94 occur in nature. And well, 24 are artificially produced. And these are basic building blocks of matter. And these, of course, then form like various chemical compounds, which are 10 million that we know today. So these, of course, then are formed through chemical reactions. When the elements react with each other, they form the compounds. And the compounds or what everything is made of, basically. It's like very rarely it's only a single element forming something that we use or what we are. So substances are converted into other substances, of course, when in the chemical reactions, it's not only elements reacting, it can be also some kind of chemical compounds reacting with each other and forming different kinds of chemical compounds. Electron distribution of atoms and molecules change, and bonds are formed or broken. And of course, the atoms, each individual atom in a compound wants to gain the lowest energy possible. This was the reason why the bonds are being formed between atoms and why chemical reactions happen, mainly. Atoms can also turn into ions, and molecules can combine or disintegrate and are, of course, rearranged. Here is just some kind of a picture that I found from Wikipedia of a thermite reaction. Okay. Yes. So here is some kind of a picture that I again found different types of chemical reactions. So you can see that you can name them in many ways. And then these things, we just here talk about basically like chemical reactions as a topic for this and next week. And we don't go into what kind of, if it's synthesis, decomposition, single replacement, double replacement. Maybe some of you already know something about this, and maybe you will then later in these studies and in your profession will know more about that. So we were talking about the atoms forming bonds with each other, like covalent bonds, ionic bonds, and this happened, of course, through the chemical reaction. And then, of course, a chemical compound is being formed. It can be solid, liquid, gases, and that depends on its molecular structure and the nature of the bonds. So we have the reaction equation, where we have the initial and final states of the reactants and products. And we have to balance that. This reaction can be endothermic, which means that it binds heat, or exothermic, and so that it releases heat. And also the reaction rate, which means like the speed of which the reaction happens, is important. It depends on the reaction conditions, the reactants, temperature, and use of catalysts. And here is a reaction equation. Yes, sorry, this picture in Finnish. But you can see that there's oxygen with hydrogen, one oxygen, two hydrogens, and we form two molecules of water and gain energy. These are reactants and these are products. And then here is the arrow. We think that it progresses from the reactants to the products. Many times it, of course, goes both ways. But sometimes also just from the reactants to the products. That would be pretty simple, and that's also something that sometimes we would like to happen. Yes. So here, two hydrogen molecules react with one oxygen and form water. I will do now something here and we will check this one very, very little short clip, video clip. Okay, sorry, these texts are in Finnish. So this magnesium reacts with a hydrochloric acid. And the gas that's formed there is hydrogen gas. So that's what's happening now. And because the hydrogen gas is lighter than air, it rises and you can store it into this empty pipe. And now when you turn this pipe tube upside down, the hydrogen gas tries to escape again from there because it's lighter than air. And now with a little bit of heat, you get a reaction. We didn't have the, so the hydrogen gas burned, which meant that it reacted with water. And now you can see that there was a water being formed. And here is this reaction, the reaction that we were talking about as well. Good. That was a short video clip. Okay, so it was a chemical reaction between oxygen and hydrogen, which is called combustion reaction. Burning hydrogen, so hydrogen reacting with oxygen. And then some bonds, there were some bonds, and those bonds were broken, and another kinds of bonds were being formed. We were talking about the bonds here, covalent bonds in these molecules of oxygen and hydrogen. These bonds are being broken. And then another kinds of covalent bonds are being formed between hydrogen and oxygen in the water molecules. And those were these kind of polar covalent bonds. And of course, the atoms are arranged in a new way. And then there are two elements in each molecule here. Here, these were just like single element molecules. At first, now there's two elements together. And it's a it's called a chemical compound. It's not a pure element. And you also then create energy. And this is what you usually create in combustion reaction. We will talk about the combustion then later on the course more. But here is just as an example of chemical reaction. So combustion reaction of methane. And there is 4 atoms of hydrogen that are there in a molecule together with carbon. And we need 2 molecules of oxygen, where there's 2 oxygen atoms bound together. And then we form carbon dioxide and water. And this is called like total burning or pure burning. When we just form two compounds, which is carbon dioxide and water. Well, the total mass after the reaction is the same as before reaction. So the total mass, we didn't lose any of these compounds here in the reaction. And then, of course, the reaction when you carry out in the closed vessel, this is what happens. Of course, you might lose something if something just happens and then something escapes to the air, like the carbon dioxide. And this is the law of the indestructibility of matter, or conservation of mass. That sounds a lot nicer, maybe. Mass remains unchanged in a closed system. So total mass of the reactants is equal to the total mass of the products. And this is a fundamental principle of chemistry. And yeah, the mass is not created or lost, but it changes its form, like also the energy. Energy in the law of energy conservation. So you have to then balance the number of atoms, of course, so that it's the same on the both sides of the arrow. So in the reactants and in the products. So you write the equation, reactants and products as chemical formulas. You count the number of atoms of each element in reactants and products, then you balance. And you can start it with an element that is present in only one compound on each side of the equation. And you use multipliers. You put numbers there to balance the number of atoms. And then calculate that you have the same number on both sides. And here is an example. Here's the burning of methane to form carbon dioxide and water. And then when you write it at first with the chemical formulas here, and then count in reactants and in products, now you seem to have different amounts. So here, for example, well, there's only one carbon, but then hydrogen, here you have 4, because here is the number 4. But here you have only 2. And then also oxygen, here you have 2. And here you have also 2, but here still 1. So that's 3 in total. What then you need to do is start writing numbers into the equation so that you get it balanced. So for example, that if you start with the hydrogen that was present only in one reactant and in one product, which would be the methane, and then the water, then you can easily balance it by putting 2 in front here. So then it's 2 times 2, which is 4. So 4 on both sides. And now then you have to also, of course, balance the oxygen. So here you had then 2 oxygens, and also here 2 oxygens. So you have to write 2 in front of the oxygen as well. Then you check, and it's balanced. Pretty simple. Balancing the electric charge. This we won't be actually practicing on this course. Maybe on your next chemistry course, you'll be then practicing this as well. But you also, when you have their ions reacting, which is many times the case, and you also have some ions forming, you also have the balanced number of electrons. So you have to calculate that you don't lose or gain electrons in the reaction. But this is something that we don't really have time to do on this course. Okay, so about chemical reaction, there are these types of endothermic and exothermic. The endothermic meant that you need heat to get the reaction to happen, basically. Or heat is bound from the environment. For example, photosynthesis, where you need the solar energy to carry it out. And of course, other things like the reactants. So carbon dioxide and water, and then you form something where energy is being bound, and that can be used then as a nutrient. And then also produce oxygen to the air. So this is the vital reaction for the life on Earth. Of course, you all heard about this already earlier, but this is here as an example of endothermic chemical reaction. Yeah, there was this, when I did this slides with the AI, it suggested me as a chemical reaction, this melting of ice. Of course, you need energy to melt ice, but it's not a chemical reaction because there's nothing new being like produced. There's only the water in the solid state or liquid state, and in chemical reaction you actually form something. You don't have the same compounds on both sides of the arrow. So of course, if you have an endothermic reaction, it does not occur spontaneously, but it requires external source of energy. And then the opposite is the exothermic chemical reaction, where you release energy. You can produce heat, for example, like in the combustion. And it can occur spontaneously. Well, it usually increases the entropy. And combustion is the example. Or then neutralization reaction, which we have here. So you have hydrochloric acid and natrium hydroxide. Sodium hydroxide, yeah, it's called sodium in English. And you produce salt and water. So in neutralization reaction, you usually have an acid and a base. And this is something that's important to you in practice at work. So if you have some kind of liquid coming from some process that's either acid or like it's a base, then you have to neutralize it, and you get water and salt. And depending which acid and base you have, it depends which salt you get. And you usually get the salt as a precipitate. And this is also exothermic reaction. So you can also produce heat there. Or then this thermite reaction that we had a picture. And here is the equation for that. So you have iron oxide, and then it reacts with aluminum, and you get poor iron and aluminum oxide. So usually the metals are being bound with something. For example, this iron with oxygen. So if you need pure iron, you need to do something to it. You can, for example, use this thermite reaction. And here you also produce a lot of heat. And of course, the exothermic reactions are important. Practical applications, heating engines, industrial processes. Yes. Reaction rate. This we don't talk much now, but we still, like I mention it because it's important in practical reactions. So if you have some really, really slow chemical reaction, you can't, of course, use it in any application. You have to do something to the slow step, add a catalyst or something. So some reaction might happen, but if it happens really slowly, it's not practical and you have to do something to it. Reaction rate describes that, how fast the reaction happens. And it's influenced, of course, by several factors: concentration of reactants, temperature, pressure, and catalyst. The catalyst, if you add it there, it might take some other step, react with the catalyst, and then form the products and release the catalyst and avoid the slow step. Okay, so here's just some chemical reactions, and then you get some products. And here's, for example, a reaction again. So this is the opposite to the one that we had earlier. So you have the glucose and oxygen, and then they form carbon dioxide and water. This is, for example, what happens in our body when we use the glucose as energy. So you write the reaction equation, the reactants and products, count the atoms, balance, and check. And here also you have had to add some numbers here as multipliers to get the correct amount of those elements there. Why are the coefficients then needed? Well, molar ratios of substances are expressed by these coefficients. And there we get the ratio in which molecules or ions of different substances participate in the reaction. So we know how much we need to put some reactant and how much we get the product. So if we know how much we want to get some product out of the reaction, then we of course need to know the molar ratio. Here is, for example, methane has a molar ratio of 1 to 2 with oxygen. So 1 mole of methane reacts with 2 moles of oxygen. And you get 1 mole of carbon dioxide and 2 moles of water. So we can then use the moles, the amount of substance that we were practicing on the last lesson. So here's some examples of this. And these are the examples of the book, but translated in English. So glucose is converted to ethanol. And also carbon dioxide is being released. And if we write the chemical equation, and this is called fermentation, reaction of glucose. And so we know, first of all, the glucose equation. Then we know the ethanol and the carbon dioxide. Now we have to balance so that the number of atoms of each element is the same on both sides. So then we would calculate from here how much we have which. For example, the carbon here is 6, so here we would have 4, and here 2 more, that's 6 in total, and so on. Well, then the physical state symbols of the equation, many times we need to know this, usually always. So, for example, to have the glucose to ferment into ethanol, you have to have it in water. This agu here behind it means that it's in agua, which means water. So it's a solution of glucose with water. You get a solution of ethanol with water, and the carbon dioxide doesn't stay there. It goes to the air as a gas, like it goes in the combustion reaction as well. And then when we do enough combustion, we manage to get climate change with too much carbon dioxide in the air. Okay, so then how much carbon dioxide, many times we might be interested in this, is released if 1 kilogram of glucose is completely fermented into ethanol. So also in this kind of a fermentation reaction, we manage to produce carbon dioxide. And we know that 1 kilogram of glucose we make into ethanol. So now we can go to this amount of substance calculations, where the amount of substance can be calculated by dividing its mass by its molar mass. And here, a molar mass of this glucose has been calculated with the molar masses of all the elements, multiplying them with these numbers, how many there are in the substance. And we get how many moles we have in 1 kilogram. And then we need the equation here. So each mole of glucose produces 2 moles of carbon dioxide. We can see it from the balanced equation. So here 1 produces 2. So then we know easily the amount of substance, amount of carbon dioxide as this amount of substance as moles. You just have to multiply it with 2. And then we could calculate the mass, or here if we want to know the volume, we can use molar volume of ideal gas. So the amount of substance is also, for gases, volume divided by volume of like how much volume 1 mole of ideal gas needs. And then we can solve the volume that we get. So for example, in this fermenting 1 kilogram of glucose into ethanol, we get 270 cubic decimeters, 270 liters of carbon dioxide gas. That's, well, also something. Okay, and then the next example of the book. How much nitrogen gas is produced when 100 grams of sodium oxide, which is this kind of a compound. So there's sodium and nitrogen. This decomposes into sodium and nitrogen if this kind of a reaction happens. So I just know that somebody tells me this kind of reaction happens and I have to balance it. Oh, there is some kind of a weird thing there. Okay, I can calculate the molar mass, and from that I can calculate the moles, the amount of this reactant. And I also, I knew the mass already. I get the moles, and then from the molar ratio, so now I get from 2 moles of this reactant, I get 3 moles of this product that I was interested in. So it's more. From this, I get a little bit more of this. I need a molar ratio here. So the ratio is 3 to 2. And multiplying with this, I get the moles. How many moles I get the nitrogen. And then again, it seems like I was interested in the volume, which many times when some gas is being produced is the case. And this can be also solved using the ideal gas law, which is of course a bit weird always, these ideal gas figures, but many times these are like close to the reality. Or then you need some kind of correction factors there in your real like process. But anyhow, here's the ideal gas law. For sure, you know the ideal gas law, maybe from you've been using it in the physics course or somewhere where you can then calculate the volume. So there's the amount of substance, this R, the temperature you need to also know in this, and then the atmospheric pressure. Those are the examples of the book. Well then, here is scanned somehow this where you find these things from the technical formulas book. There is the amount of substance formula, ideal gas law. What else? What else? Well, basically those. This is not so great, this chemistry section of the technical formulas, but it's okay. The concentration, yeah, you can find the concentration. Concentration, what does that mean? Is the amount of substance or amount of certain substance in a solution divided by the volume of the solution. This is always for some kind of solution. And here it's being explained as well. This is a chemical quantity, describes the concentration of a solute in a solution. So how much substance is present in a given volume. And the units is moles per liter or moles per cubic centimeter. And then there are other concepts as well, but you get to know these then on other courses. On this course, we use the concentration as moles per liter. And here is the figure explaining this better. So the concentration of a solution is the quantity of a solid that is contained in the particular quantity of solvent or solution. So there, of course, in the solution, there might be also other substances. You are now interested in the concentration of a certain substance. Then here you can just see that, well, low concentration, you have less the substance, and high concentration, you have more. And, like the Avogadro was calculating the moles. For example, like the units of the substance. So there can be more or less. Moles per liter, moles per cubic decimeter, or just this kind of big M. It can be also expressed. This is also something for sure you'll see then. Reaction equilibrium is also this to do with the chemical reactions, because we were talking about the chemical reactions that had a single arrow from the reactants to the products. But this is not, of course, many times the case. So usually if you put some reactants to the solution to react together and you aim to get the products, you end up in a situation where there's everything present there in that solution. So you have both the reactants and the products, and it stops to some kind of equilibrium where you have it all. And then you need this kind of constant K, which is called equilibrium constant. And this will describe you the composition that is there in the equilibrium state. And it's temperature dependent, so sometimes when you heat up the solution or cool it, then you can get it more to the products or more to the reactants, depending on the reaction. So initially you stick the reactants A and B into the container, into the some kind of a vessel, and you mix it. And you want to get these products C and D, but you end up in equilibrium where you have them all there. So at first you have the reactants, which are starting to form the products with time. And at equilibrium, you have less of the reactants, of course, more of the products, but then everything there anyway. This K you form with the reaction equation. So you have to know of course, these reactants, the products, you have to balance it. So you have to put there the multipliers. And then you can do the K. And in the K, you have the multipliers here as the powers. Then as a numerator, you have here the concentrations of the products. And as a denominator, you have the concentrations of the reactants. This might seem a bit complicated, but it's not that complicated. And you can find this case for certain reactions that you need to know with certain temperatures that you use in your real life processes from literature, or for sure you have them there to use, and you can check what you should do. So here is an example. For example, this kind of simple reaction, you have nitric oxide, oxygen, you get nitrogen oxide from this. Here the K written for it. So here is and here also this is a bit like, okay, gas. Why not? You have a mixture of gases. You can have them also marked as a concentration. So here's the concentration of this product, nitrogen dioxide, and here is the power, that was the multiplier. And here the concentrations of the reactants, and there's also one multiplier as the power. Then if you know the concentrations and you mark them there, and you get some number. And then you can say from this number what happened now. If you have there the reaction that went through to the reactants, or if you have everything there in the vessel. And now you can compare it to this. The reaction is, if it's K is more than 10 in the power of 4, which is of course 10,000, quite big, the reaction is practically products. But if it's from the 10 in the power of minus 2 to 10 in the power of 2, which is 100 to the 100, the mixture has everything there in the vessel. And then if it's less than 10 in the power of minus 4, there's no reaction at all. So you just end up having the products, the reactants there in the vessel, no products at all. Okay, so here we got the 80, which would mean that in the equilibrium state, the concentration of products is higher than the concentration of the starting materials. So this is like, but you still have the reactants there also. Okay, this is only in Finnish now, and this is from the book, and the book goes through this thing, but of course in Finnish, what there it was gone through already in English, so you don't have to look it from the book anyway. And here is also an example. This in Finnish, but you can see there's the concentrations. You have calculated the K, you got something from there, and then you can compare it, what happened here. So obviously in this reaction, you also got products, a considerable amount, but you also have the reactants there in the vessel. Okay, so then we have this Le Chatelier principle. It's a chemical principle that describes how the state of equilibrium changes when reaction conditions are changed. So if you are interested carrying the reaction through to the end, and you realize that it didn't go through and you still have the reactants, you have to change the reaction conditions. So if an equilibrium system is subjected to an external change, such as change of temperature, for example, pressure, concentration, the system tends to resist this change and reach a new equilibrium state. Okay, sounds a bit complicated. But for example, if you add heat to a reaction that is exothermic. So if your reaction is already releasing heat, you add heat, you get more reactants. For example, here. So from nitrogen and hydrogen, you can form ammonia and release energy. Sorry, this is in Finnish. And now, if you add here more energy, you get more of the reactants, so you don't actually end up to the products. So to get more products, you should cool it down. It tries to reduce the effect of the added heat if it already produces heat and you add heat. So it wants to absorb the excess heat and reduce its effect. Here's some other example that you can also read. Then in the production of ammonia, the required hydrogen can be produced from methane using steam. Methane, steam, you get carbon monoxide and hydrogen. This is one way to get hydrogen as well. If you add hydrogen to the reaction mixture, what happens? So of course, if you add a product more, the equilibrium goes towards the reactants. If hydrogen is removed, well, then you get more products. This tries to produce them more products. So it's good to remove the products, take them away, and then you get more of them. So if the pressure is decreased by increasing the volume, and here you have the moles of the gaseous substances. So here you have 2, and here you have totally 4. These take more space. If you give it more space, you get more products. And you improve the yield of hydrogen again. So removing the hydrogen from this, you improve the yield. And then also giving this more space. So increasing the volume, you also get more products. And you shift the equilibrium towards the products. Then there's still this kind of this is this kind of process, Haber-Bosch process. Just an example. You have this is as an example in the book as well, where you can alter the conditions and then do something. Something there, so you can produce the ammonia basically from hydrogen and nitrogen. But this is, maybe you'll get familiar with this in your actual applications then later on. Then there was still this precipitation reaction, chemical reaction in which two aqueous solutions react to form an insoluble solid that forms a precipitate. Precipitate means that it precipitates in the bottom of the vessel. Ionic compounds that are dissolved in water combine to form a poorly soluble compound. So the neutralization reaction was one like this. Here is also another example of precipitation reaction. Silver nitrate and sodium chloride react to form a silver chloride precipitate. And that forms at the bottom of the solution as a solid. These are widely used in chemical analysis. Chemical analysis you might be then practicing later. So you can then decide the amount of the precipitating substance by weighing the precipitate. This kind of analysis, I think I've done at some point as well as a practice. And then, of course, in the applications, sometimes you don't want some precipitate to be produced so that it doesn't block the pipes. So, or if it's being produced, you need to know that it's there to remove it somehow. Here again, two liquids react together. They form a solid precipitate. Here is another example of chemical compounds that you mix and you get a precipitate. Oxidation reduction reactions then are also chemical reactions. Redox reactions. So oxidation number of zinc, for example, here increases. And then the copper is being reduced. So it means that you have these metals, noble and non-noble metals. I think I have well, no, I don't have actually this here, but this will be later then when we have the electrochemistry. So, well, one substance basically just donates electrons to the other substance that receives them. And you can get like pure copper, for example, from some solution of a copper. Okay. Yes. So then we go to the other screen. And I will still do a couple of examples there. So of the exercises of the chemical reactions, here we will practice how to determine the coefficients of the following reaction equations. We can do that then there in the class. But for example, how to write the combustion reaction of iron, which means the reaction of iron metal with oxygen gas. The combustion meant the reaction of with oxygen, basically. How many moles of oxygen are needed if the amount of iron to be burned is 4 moles or 1 mole? And this we can decide through writing the chemical reaction equation. So this would be our chemical reaction and exercise 2. So then I write here the combustion reaction of iron, which means that iron, of course, reacts with oxygen gas. Oxygen gas is always like this. There's two oxygen atoms bound together with a covalent bond. And we get iron 2 oxide. So we get iron oxide, iron 3 oxide, sorry. Okay, how many irons and how many? This is iron 3 oxide. And now we need some letters there. We should know what is iron 3 oxide. Of course, we can Google it. Or then we can check this. We know some things, and we can check, for example, from the technical formulas. The element and the most common oxidation numbers, which for oxygen here is usually always in the substances that it forms, -2. So then, if the oxygen O I checked is -2, and then the iron is +3, because this 3 here means that it's the oxidation number is +3. You can also check it from here. Iron +2 or +3, either or. But it looks like the +3 is more favorable because this is in bold. And it's here also +3. So now we have to make this neutral outside because it's a compound. So we have to multiply this. And, well, whatever. We have to multiply this, of course, with 3 and this with 2 to get it neutral when we calculate them together. So -2 times 3 is -6, and plus 3 times 3 times 2 is also 6. So -6 plus 6. That still fit it there. This would be -6. This would be 6. If we add them together, then that's, of course, 0. So we can put these numbers there. The oxygen was 3, and the iron was 2. And now we have iron 3 oxide. And then now we can start balancing the reaction equation here. So it looks like there's 2 of these. If we put here 2, we would have that balance. But then there would be a problem again. So there's 2 and there's 3. So to balance the oxygen, we actually have to put here 2 and here 3, yes? Because 3 times 2 is 6 and 2 times 3 is 6. So now it looks like we actually need a number 4 here, yes. Let's put there number 4. And now we have the balanced reaction equation. And now we can go to the calculating how many moles. And in the part A, there is 4 moles of, how many moles of oxygen are needed if the amount of iron to be burned is 4. So I would mark it like this. The amount of iron is 4 more. And then I can check from here. So obviously here my multiplier is 4, which is how many moles of oxygen I need. It looks like that it's 3. Amount of oxygen gas is 3 moles. So, and then in the part B, if the amount of iron to be burnt is 1 mole. So then how many moles of oxygen I need now? So I have to check it again from the equation here. So I have this kind of ratio. The ratio of the oxygen that was in questions to the ratio of the iron from the equation is 3 to 4, which is 0.75, yeah. I can also see it here. If I have 4 of this, I need 3 of this. The ratio of, so it's obviously the ratio of 3 to 4, 0.75. So now if I here have 1, then that would be the amount of oxygen would be 0.75, yeah? Or I can also mark it like this. The amount of O2 is the 3 to 4 ratio to the amount of the iron, which was 1 mole. 1 mole, which is 0.75 moles. Okay, let's take another example still. So then there is this, I want to produce iron now. So now at first I was burning iron to get iron oxide. Okay. Maybe in the practical terms, I would like to usually maybe produce iron from iron oxide. And here I can also see, here is the chemical formula already. If this reacts now with carbon, so that I can gain the iron, the pure iron, and I again produce carbon dioxide, how many kilograms of carbon I would need to produce 1 kilogram, 500 kilograms of iron. Okay. So again, I need the equation here. So I'm producing iron. And this iron oxide, iron 3 oxide, reacts with carbon. I can put carbon as just C there. And I form carbon dioxide and iron, of course. So the iron is what I wanted. And as a side product, I also get the carbon dioxide. And now I have to balance this again. So the C's seem to be fine, but the irons no. And then there's still the oxygen, which is here 2 and here 3. So if I put here 2, and then I get the irons balanced, but then I have a problem again with the oxygen. So it looks like I again need here the 2 and here the 3. So that I get the oxygens balanced. And then obviously here I need actually 4. And now I would have the balanced equation for the reaction. So then I would know that I want 500 kilograms of iron, which means that my mass of iron, the pure iron, is 500 kilograms. And now for this to know how much carbon I need I need to know the amount of substance for this. The amount of substance was, of course, amount of substance. That was marked as N, and that was the mass per molar mass. So now I need to know the molar mass also for the iron that I can find from the technical formulas. The technical formulas chemistry was in the end pages. Here elements 185 page, and there is iron there, and this is the molar mass, 55.8. So I write it there. So, and this is grams per mole. Grams per mole. And now I know that it will be quite a lot. This is also in kilograms. So I can also write it as kilograms per kilomole. It's the same. This is how many kilograms it weighs for a kilomole, which means this is the multiplier of 1,000. Yes, good. So now I know the amount of substance for the iron, which was marked by the N, which was mass divided by molar mass, which is 500 kilograms divided by 55.8 kilograms per kilomole. And now I get how many kilomoles of iron I have in 500 kilograms. 500 divided by 55.8. And this would be 8.961. I can round it from here. Kilomoles. So now I know this, and then from here to get 4, oops, now there is something wrong here. I have forgotten one multiplier, which is the multiplier of the carbon. This is not balanced here. Now I can see before I make any calculations more, then I have to put there, of course, the 3 there, because there's, with the C, there's 3 CO2 3 to balance the carbon as well. This is lacking this. Okay, so to get 4 of iron, I need 3 of the carbon. So I can also write it like that, like I wrote the last time. The amount of substance of carbon is, there's the 3 to the 4 ratio to the amount of substance of the iron. And now I can calculate it, because I know the moles of the iron. So it's like 0.75 times this, yes. You can see it from the equation here. If this is 4, this is 3. But I can mark it as 0.75 or 3 divided by 4. Okay, moles. So here I have this accurate number. I can just multiply it with 0.75. And I get how much I need, the how many moles I need the carbon. K moles. And now to calculate this and into kilograms, I still need to do the similar modification from this equation here. So the mass of carbon then, of course, is the moles times the molar mass. This is supposed to be the big M. Moles I know, 6.72 kilomoles. And I can multiply it with the carbon molar mass, and this was here again. Carbon there, which is 12. 12 grams per mole or kilograms per kilomole. Yes. So I can multiply this with 12. Whatever. There, and I get how many kilograms I need. There would be 80.65 kilograms, about 81. 81 or 80.6 kilograms of carbon. Okay. So there's actually some of us even present here, not only me. I will now finish the recording.